Since this week's topic is the engine lathe, we're going to go over the parts of a lathe, not just for your understanding during the video, but also because when I talk about a lot of the different concepts, turning, facing, drilling, threading, feed rates, surface speed, spindle RPM, these concepts are all going to require you to have a fairly basic understanding of the parts of the machine. So that's where we're going to start. This is a 15-inch engine lathe, and it's named so because 15 inches is the largest diameter workpiece that can be mounted on the machine. Typically, the machines aren't used at their maximum capacity, but it does happen occasionally. So the structure of the machine is really this long piece of cast iron here called the bedway. And the bedway aligns all the pieces of the lathe so that the workpiece comes out cylindrical and straight. The bedway is a really precise surface, and so even though it's horizontal and looks like you'd set things on it, you wouldn't. It's fairly delicate. Mounted on the bedway is the tailstock, and the tailstock slides back and forth, and we use the tailstock for drilling operations as well as to support long workpieces. Also riding on the bedway is the carriage, and the carriage moves left to right. It moves forward and away from the work holding apparatus, which we'll get to in a second. The carriage contains an apron. The apron has controls for activating the automatic feed, which we'll talk about, as well as for activating the threading functions of the machine. We'll talk about that once we talk about lead screws a little bit. But the carriage moves left and right in the Z-axis, which is the axis that is in line with the spindle center line. Mounted on top of the carriage is the cross slide. The cross slide moves back and forth in the X-axis, which is perpendicular to the Z-axis. Then on top of the cross slide sits the compound, and the compound can swivel so that we can cut tapers and angles and chamfers of any angle on the workpiece. So we call it the compound because it compounds an angle upon the two directions which we can move with the cross slide and the carriage. Now ultimately all of this movement is dedicated to moving this right here. This is the tool post. And when I get the camera up here, we'll look at the tool post and the tool holders a little bit more closely, but this contains the cutting tool, which is what's actually doing the work. So these are all controls for very precisely moving the cutting tool itself. There's also a threading dial here and a engagement lever. When the spindle, when you're ready to start the spindle, you pull up on this lever to engage it. As we continue along the bedway, we get to the headstock, and the headstock contains all of the gearing and controls for setting the spindle speed. The spindle itself is right here. This spindle, where it comes out of the headstock, is onto which we mount our work holding apparatus. So in this case we have a dependent jaw, 3-jaw chuck. It's called dependent because when we turn this chuck key, you'll see that all 3 jaws move together, and you'll get a better look at that when we actually mount a workpiece up here. But the chuck is mounted on the spindle, which lives in the headstock. So the tailstock is at one end of the bed, headstock at the other. The headstock contains the controls for setting the spindle RPM, the speed at which this chuck is going to turn, as well as emergency stop functions. Below the headstock sits the gearbox. And the gearbox is what allows us to change the speed of the lead screws. So underneath this stainless cover right here, you'll see a pair of screws of shafts that run longitudinally the length of the bedway, and through the spindle we can transmit power to the gearbox. When the gearbox is set properly, it will turn these lead screws. We can engage them and move the carriage and the cross slide at a very specific predetermined rate. We'll talk a little bit about speeds and feeds when we talk about surface speed and things like that. But just to go over the parts of the machine, the gearbox runs power to the lead screws, which are then connected to the apron to move the carriage and the cross slide. The first step in machining our workpiece is going to be to clean off this soft finish that's on the end and then center drill it so that we can support long workpieces. I mentioned that the tailstock could be used to support long pieces. The reason we need to do that is that as we're machining this, the force of machining is going to want to deflect the long workpiece away. So by machining and putting a special tapered hole in here, we'll be able to support the workpiece and keep it from deflecting. So I'll chuck up the workpiece here in the 3-jaw chuck. And then I'll come across with a high-speed steel cutter, and then the last thing I'll do is bring in the center drill, which is the special tapered drill that is going to create the feature on the end, which will be supported by this live center. So this is ultimately what is going to sit in the hole made by the center drill and support the long workpiece. Good. For the first pass that we make along our workpiece, I've got the camera set back a little bit so that you can actually see me operating the controls. You'll see me in feed with the cross slide, with the spindle on. I'll engage the feed rate, and then I'll be watching this digital display to actually track how far we're going. Each section is going to be 1 inch long. The consecutive passes, I'll have the camera mounted up here so you can get a little bit better look. So I have my gearbox set at 540 RPM and then 10 thousandths inches of feed, which is what we have set for our first pass. The goal of today's activity is to observe the changes in surface finish that come from the different parameters on the engine lathe. And so we need a way to evaluate that surface finish. This gauge is called a comparative surface finish gauge. It has listed a number of processes and then scales for the varying levels of roughness that you can get. As we progress through today's activity, I'm going to pause in between each pass, and I'm going to use this last scale right here for turning to evaluate how smooth the finish is. I'll do that just by feel, and then that'll give us our data to finish our discussion about the impact of the parameters on the process. So now I'm going to go through the remaining 3 cuts for high-speed steel. I'll pause in between each one to collect my surface finish data, but what's going to change is the feed rate and the spindle speed for each pass. I'll probably fast forward through these because they'll take a little bit of time. Okay, we've set up for doing the other 2 sides, which were sections D and E. We've replaced our high-speed steel tool with a carbide tool, and now we'll make our 4 passes here to cut sections D and E. So 4 sections, that'll be 2 different feed rates and 4 different RPMs, because again, every time we reduce material, we have to increase the RPM to maintain the same surface speed. The last section of today's activity is section C. And section C is not done with a chip making process necessarily, but a forming process. So far all the tools we've been using have been cutting tools, but this tool is a knurling tool, and its job is not to remove material, but instead to deform it. And so there's 2 hardened rollers, and they have patterns on them, and they will roll together, and they're going to impression into the material. And instead of cutting away a chip, they're simply going to displace that material. You'll see immediately that this surface will actually start to appear to be growing in diameter. The reason for that is that we're not cutting any material away. As much as these rollers impression material in, they pull material back out. So now this probably looks quite familiar to you. This is standard knurl. You see this on all types of hand tools, barbells, things like that. And now you know how it's made. It's not a cutting process. You can see the surface is raised a little bit here. And each one of these rollers makes half of that diamond pattern. I'd like to wrap up today's activity by just looking at the data that I collected. So you all saw me operate the engine lathe, and you should have a pretty good understanding of how feed rates and speeds work, as well as how some of the basic hand controls work. The goal of today's lab, though, was for you to actually make observations about the difference in surface finish that you would get from different cutting tool materials and different feed rates. All the math we talked about calculating these RPMs was really meant to rule out surface speed, because surface speed really was not changing. Look at the surface speed calculations in this column. Because we increased the RPM as the diameter decreased, we were able to maintain that as constant. The goal was to rule that out as a factor. So when we look at the factors that did change, really the biggest factor that had influence on surface finish, which I have over here, was feed rate. And that really makes sense, right? Because as this cutting tool is moving across the workpiece, it's generating those peaks and valleys. And the distance it moves each time is the feed rate, right? For each inch, for each revolution, this tool advances some number of inches. When you look at these, you'll see that for the finer feed rates, we actually have better surface finishes. So down here where it's the worst surface finish, 6.3 microinches, we have our highest feed rate, 0.016 inches per revolution. There's one outlier here that we got a slightly better surface finish with a little bit coarser step over or feed rate. Here 8 thousandths feed rate instead of 5 thousandths. We wound up with a better surface finish. And I just wanted to point out what may have caused that is that the radius on the end of the carbide tool is larger than the radius on the end of the high-speed steel tool. So the high-speed steel tool may have been making smaller, deeper grooves, whereas the carbide may have been making broader grooves, thus making it appear to have a better surface finish. But overall, the goal of this week was to give you the experience of seeing these factors in action.